Okay, well, we are about to look at question number 5 from the 2024 AP Calculus BC exam. I am solving this in real time. I have not looked at the question yet, which means I might make a mistake or I might have to pause to process the problem a little bit. If you see any mistakes, make sure to comment those below, and I'll respond to the comments with, yes, that was a mistake, or no, I feel very good about what I said. So let's see, number 5, looking at this, let's see, we have a function that's twice differentiable, values of f prime are given. We have an integral defined function, find the value of h prime of pi, show the word. Okay, so question A, this so far doesn't look bad. It's going to be like a function analysis type thing. Ooh, there's an Euler's method. I like to do Euler's method with a table. I don't think a lot of teachers like to do it that way, but I just make more sense of it that way. Let's see, so h of x is that. I need h prime of pi, so I'm going to start by finding h prime of x. And that will be done by substituting the x in the place of the t. This is your fundamental theorem of calculus, finding the derivative of an integral defined function. And it's going to be the square root of 1 plus f prime of x all squared times 1. And why am I multiplying by 1? Because it's a good habit to always multiply by the derivative of the variable expression that replaces to the t's. In this case, that's just a 1, so it's not that big of a deal. And then find the value of h prime of pi and show the work that leads to your answer. So h prime of pi is going to be the square root of 1 plus f prime of pi all squared. And I assume f prime of pi is in that table. So 1 plus f prime of pi is 6 squared. And you would stop there, but if you want to show off, you can call that the square root of 37. If you do simplify it, I would recommend putting a line through it just in case you made a mistake, and that way it won't be held against you, and the reader will look back at your last unmarked out step. Number B, what information does that provide about the function f? What an interesting question. It's interpret the meaning of this integral is how they usually ask that. Interpret the meaning of, and you look at the integral setup, and you should recognize this integral setup. 1 plus the derivative of your function squared. You should recognize that as the setup for arc length. It's the length of the curve. And so I'm going to type out my interpretation or explanation of what this is. That integral provides the length of the curve f of x on the interval 0 less than x less than, I'm just going to actually type the word pi because I don't have a hot button for pi on my keyboard. That provides the length of the curve f of x on the interval. Yeah, that's it. Number C, Euler's method. And I like to do Euler's method with a table. So I'm going to set up my table here, and I'll make my table kind of big. Let's see, probably at 2 steps. It's always 2 steps of equal size. Well, yeah, 2 steps of equal size, so nothing different there. So we're starting at the known coordinate at x equals 0, and they tell me up at the prompt that f of 0 is 0. So there's my initial x, there's my initial y, my delta x. Let's see, I'm going to draw out my table. I need 2 steps. I'm going to approximate f of 2 pi. Okay, so my delta x is going to be 2 pi minus 0 divided by 2, which is just pi. So my delta x is pi, so I'm going to go from 0 to pi to 2 pi. And then for my change in y, I know that my derivative, I'm going to put a line separating parts B and C so they don't bleed together. So my derivative, dy dx, is f prime of x. And if we, hang on just a second. All right, so, and now if I multiply both sides by the dx, and I turn my dy dx into delta y delta x, I find out that delta y is f prime of x, delta x. And so that's what I'm going to put down here. Delta y is f prime of x times delta x, which is pi. So I'm going to replace the delta x with a pi. And then I like to put another column over here on how I am computing my new y coordinates. My new y coordinates are my previous or my old y coordinates plus my newly found delta y. And now we start working this out. So f prime, I need f prime of 0 times pi. F prime of 0 is 5 times pi. And that's my delta y, which means my new y is going to be 0 plus 5 pi. So I just found my new delta y. which put me at a delta y, or a new y of 5 pi. Now for my new delta y, I need f prime of pi times pi. And I go back to my table, f prime of pi is 6 times pi. So I just found my delta y, so I need to add that to my previous y's, and that'll be 5 pi plus 6 pi, which is 11 pi. And then I'm going to very clearly state that f of 2 pi is approximately 11 pi. So we've stopped right here. One of the dangers of you doing the table is sometimes you hit a groove and you want to fill in this last row completely. But once you get the y coordinate that corresponds with the x of 2 pi, you have your approximation. So this is where I stop on part C. And then part D is a indefinite integral, and show the work. You don't see these very often in free response. That's interesting. These are usually your multiple choice type questions. Usually in free response, it's at least a definite integral and there's some context or whatever applied to it, or at least that's what I've seen lately. The antiderivative of t plus 5 times the cosine of, and I'm going to change t over 4 to 1/4 t. And this is going to be an integration by parts problem, and we can actually use the tabular method on this, which I will. U is going to be t plus 5. I like to call it u prime. A lot of teachers like to call it du. U double prime is 0. And if I finish with u double prime, I'm going to start with v double prime, which will be the cosine of 1/4 t. And the dt is technically part of it. I don't write that down. The antiderivative of cosine is positive sine. And we keep the 1/4 t. And this is a u sub situation. And I tell my students that this pattern shows up enough. If you have what's otherwise a recognized antiderivative, the antiderivative of sine x, of cosine x is sine x, but there is some constant with the x, it would be a u sub where u would be ax, and you would have to find the du and all that mess. But the answer always ends up being your recognized or your memorized antiderivative. You keep the constant with the x and you end up dividing by it. I'm not a huge fan of just memorized tricks like that, but sometimes if it shows up enough and it's efficient enough, I encourage students to know that. And so I'm using that on this one. And so when I divide by the 1/4 here, that will be the same as multiplying by 4. Whoops. What did I just do? Oh, I need to scroll down. There we go. All right, so now I need to multiply by 4. That's my first antiderivative. My next antiderivative, the antiderivative of sine is negative cosine of 1/4 t. I would divide by another 1/4, which means I'm going to multiply by 4 times the 4 that was already there. It gives me a 16. That was kind of wordy. I said that really weird. We do 2 antiderivatives of cosine of 1/4 t, and now for the tabular method, we multiply down, doing the positive product of those two first. That's going to be, the answer is going to be t plus 5 times 4 sine of 1/4 t minus the product of 1 and negative 16, that's going to end up being a positive 16. 16 cosine of 1/4 t plus a c. There's your answer. Don't forget the plus c. That is part of this. It is an indefinite integral, so there should be a c. And yeah, the wording makes me think that they will be looking for that c. A lot of times they'll say find an antiderivative, or they have asked that before, in which case the c is not needed, but it's never wrong to put it there. So I'm going to put it there, and that is it for question number 5. Not that bad of a question, kind of all over the place. Some very disjointed topics covered in that. Got Euler's method, we have an arc length, we have fundamental theorem of calculus up here, and then we finish with an integration by parts. So they kind of covered a lot of territory with that question.